This is going to be the lecture over sections 27.6 and 27.7. We're going to look at other concepts other than just velocity. So in order for the principle of momentum conservation to hold in all inertial reference frame, which is something that seems to be quite fundamental, the classical definition of momentum has to be modified. So similarly, in the definition of kinetic energy must be modified in order to generalize the relationship between work and energy. So the whole issue that we end up with here with relativity is Newtonian mechanics work pretty well for our reference frame here. And a lot of the principles and concepts that we have developed work pretty well. And we noticed that we can extend those to other types of situations that we need to analyze. But in order to do that, we have to make corrections. That holds true not only for distance, position, as well as time, but now other fundamental concepts are going to come into play. And how do we correct that? So when we look at momentum, we have to make a change here. We're looking at defining with momentum with this correction factor in the denominator. For kinetic energy, we're going to have to make sure that we have this correction factor in. This latter form suggests assigning a rest energy for a particular problem to a particle, so that the total energy is equal to kinetic here plus the rest energy. In Newtonian mechanics, K is equal to P squared over 2m. In relativistic mechanics, this analogous relationship between total energy of an object and the magnitude of its momentum is going to be this. So let's take a look here at these sections. So this is just a paraphrase of what I had said earlier. The principle of conservation of momentum states that when two objects collide, the total momentum is constant, provided that they are in an isolated system. In other words, they interact only with each other, not anything else. And provided that the velocities of the objects are measured in the same inertial reference frame. So if conservation of momentum is a valid physical law, then according to the principle of relativity, it must be valid in all inertial reference frames. But suppose we look at a collision of two particles in one inertial coordinate system and find that the total momentum is conserved. Then we use the Lorentz transformation to obtain the velocities of the particles in the second inertial reference frame. It turns out that if we use the Newtonian definition of momentum, momentum is not conserved. So if we're confident that the principle of relativity and the Lorentz transformations are correct, the only way to save the concept of momentum conservation is to generalize the Newtonian definition of momentum. When they say they omit the detailed derivation of the corrected relativistic generalization of momentum, they mean it. There's a lot going on there. This is really what you need to concentrate on. The relativistic momentum of a particle is always greater than the Newtonian momentum. So when particle speed v is much less than c, then it's approximately equal to the Newtonian expression. If you look at the magnitude of momentum as a function of speed, if you let the Newtonian momentum just be your definition here, you're going to end up with a variance of what you measure for momentum than if you use the relativistic definition. This correction appears so often in relativity equations that we just give it a name gamma and write it like this. So a lot of times you'll see relativistic momentum with this gamma correction next to it. What about Newton's second law, where force is the change of momentum with respect to time? How do we go about changing that? Turns out here that force is equal to gamma cubed times mass times acceleration. So it is impossible to accelerate a particle from a state of rest to a speed equal to or greater than c. The speed of light is sometimes called the ultimate speed, in other words, the cosmic speed limit. No material object can travel faster than the speed of light. You got some problems there to work through. Now, we've addressed momentum and force. What about other concepts? We need to take a look here at energy. And as it turns out, the classical definition of work, which is force times distance, can be retained. Einstein showed that when force does work on a moving body, causing acceleration and causing the object's speed to change from v1 to v2, these quantities are related again by this equation. And it asks if we might be able to define kinetic energy as this. However, this expression isn't zero when the particle is at rest, so we've got to jimmy things around. And this is what it ends up becoming. So if we went with just the Newtonian kinetic energy definition, this is what it would be. If we look at the relativistic, this is more of what we observed. And you can see these definitions here. So in an isolated system, when the sum of the rest masses changes, then there is always an equal and opposite change in the total energy other than rest energy. So in Newtonian mechanics, the kinetic energy and the magnitude of momentum for a particle in mass m are related by this. Relativistic mechanics, there's an analogous and equally simple relationship between the total E and the object and its magnitude of momentum. So this is the relativistic energy momentum relationship. If you have massless particles, this is how energy and momentum are related to each other. Massless particles, in fact, do exist. Photon is an example of one of them. They always travel at the speed of light. They're emitted and absorbed during changes of state of an atomic or nuclear system when the energy and momentum of the system changes. So again, you've got some problems you can work through there.